So, this is a skipping rope, kind of. Did you play skipping when you were young? And then did you do like random things with the skipping rope, which went like this, and just played? You're doing this, your friend is doing the same thing, and then you're playing battles with the skipping rope. There's no clear motive, but did you used to do that? Okay. So, thank you. I used to play skipping rope battle with my friend. I was very young. I was in the second standard. And then when we were doing that, slowly we started coming up with a skipping rope language. Okay. So first it was simple. It's like this means go left, this means go right. Then we'll run, mom is coming. Become more and more complicated over time. So eventually, me and my friend, what we could do is we stayed close by. We could have one end of the skipping rope in my home, one end of the skipping rope in his home, stretched across our respective windows. And then I could, signal him late at night. Tomorrow morning, let's race up the hill. Tomorrow evening, let's play cricket. We could signal each other these things. Or so we thought. It was like our personal WhatsApp group, end-to-end encryption. So one day I told him, tomorrow morning, let's race up the hill. And then I showed up in the morning. He didn't show up. Later on, I asked him, why didn't you come? He said, you said tomorrow evening, let's play cricket. I said, no, tomorrow morning, let's run up the hill. We had a big fight over this. What was the actual message? Turns out that he was receiving my signal attenuated. Okay. So the symbols were being wrongly interpreted. Okay. We are going to solve this issue today. So there is a skipping rope signal, okay, which is a sender doing things like this, okay. And then at the other end of the line, someone is receiving that signal. There could be added noise, there could be delay, and there could be attenuation, right? Which means that if I moved the rope, let's say 20 centimeters, he receives maybe half of it. If the attenuation is 50%, he receives 10 centimeters, something like that, okay? Okay. So we have solved such problems before, right? But something is unique and new here. What is it that is unique and new here? We have is attenuation the thing that's unique and new? We did attenuation when we were doing sound, right? Do you know the word attenuation? Attenuation is just like gain. Sorry, I'm using like engineering terminology, but I hope that's okay. Gain, attenuation, mathematically the same thing. Usually you call it gain when it is greater than 1, when the multiplier is greater than 1. Call it attenuation when the multiplier is less than 1. Okay. But basically it's some sort of scaling. Okay. So it is a time-based signal, correct? It's a time-based signal. Seems to be getting attenuated, delayed, all of these things similar. Noise could be added. Maybe there was wind that is adding some noise. The thing that is unique is the type of signal itself. Right? This seems a bit different than the kinds of signals that we have been used to till now. Different in what way? Yeah, correct. Every sample of the signal or every value of the signal seems to be moving around on a plane rather than being just a number. Okay? So, we will say that this is a vector valued signal. Okay? A vector valued signal, a signal whose values themselves are vectors. We thought of signals as vectors, that's different. Their values were still numbers. There were lots of numbers which made them vectors. Now we are saying a value itself is a vector. Is it okay? Now, when we were talking about just signals, I got used to representing them like this. You remember? Yes? How will we represent vector valued signals? Hmm? Yeah, but as a drawing, how will you draw it? Or as a drawing that's somewhat similar to this? Okay, these are both good ideas. Let's go with one first. Um, so, first think of it like this, right? That this is actually, so this is a number and the value could be somewhere on this line. So, this vertical line is actually the value real line of the value with this index. Now, if values themselves are vectors, then I can't plot them on a line anymore. I will have to plot them on a plane. So, imagine now, instead of a line, my values themselves being planes, right? So, you have like a rack or a sheaf of planes. Can you imagine that? Okay. And then what will a particular signal look like? You are choosing one point from every plane in that rack of planes. That is what a vector valued signal will look like. Okay? Or think of it as a, one way to think about it is like, it's like a movie where you have, if you have multiple frames of the movie, in every frame, the point is moving around on a plane and you have multiple such frames one after the other, which is what is creating a rack of frames, right? So, two-dimensional planes creating a rack of planes and specific points on each of those planes. Does this make sense? Any questions here?
So when we compare it to the earlier definition of a signal, what you're saying is now we are adding more dimensions to represent a signal. Is that what you're trying to say? When we
I'm not saying that yet. That's what he was saying, and we'll come to what he was saying in a moment. Okay? Correct. And so here I'll try to depict this rack of planes. Sorry, they didn't match up. Okay. Okay. So a rack of planes, and then in every plane we select a point. Okay, and if we want to show it as a vector, we will connect that point with a line to the origin of the plane. By the way, you know this, by the way, right? That, I mean, a vector in a plane, I could just show it as a point, or I could show it as a line segment connecting to the origin, or I could show it with an arrowhead, but it's all mathematically equivalent, right? Here was another idea. Another idea was that, hey, this plane can, or a point on the plane can be represented as two numbers itself, right? And so then why don't I think of this as just a sequence of numbers? Okay. But how many numbers will I need? I will need more numbers than I needed points in the plane. To be precise, I'll need double the number of numbers, correct? Okay. So let us choose axes and then we will project these values onto those axes. Here the projection will go here, correct? We'll project the values onto the axis and then we'll just write those values themselves. That is another, that would just be another way to represent it. Is this making sense? Hmm? Yes, so I don't know, maybe okay. So this would be another way to represent that same signal. Is it okay? So I could say that this is a signal having 3 vector valued samples, or I could say that this is a 6-dimensional vector itself, correct? It's a point in 6-dimensional space, correct? No? Now in this kind of representation, now imagine that we are trying to find out how much the attenuation is, okay? So, yes. Hmm. In this representation, we'll have consecutive vector values? No, no, no. This is one point in 6-dimensional space. No. The entire signal is one point in 6-dimensional space. The signal has 3 2-dimensional points, is one way to think about it. Or the entire signal is one point in 6-dimensional space. Yes, these two are mentally different pictures. Mathematically, there's a one-to-one correspondence between the two. Mathematically, you can convert between one and the other. See, this issue is even, forget vector valued signals. Forget vector valued signals for a moment, okay? You remember that if you just have like some audio signal, let us say. Now it has got a lot of sample values in it. Let us say there are 100 sample values. So you can think of it as a sequence of 100 real numbers, each of them representing a pressure value measured at some specific time, right? Or you can think of the entire thing as a single point in a 100-dimensional space. Single point. The entire recording is a single point in 100-dimensional space. Right? Do you understand this? Your favorite Kishore Kumar song is a single point in a high-dimensional space.
Yeah, but like, I mean, it's not the same thing as having a sequence of points, right? We are losing the time series perspective of.
Yes, you're right. Yes. We are losing the, when calling it a single point in a 100-dimensional space, we are losing the semantic information of where, I mean, how your time is going. That's correct.
We can add the time and just increase the dimensions, right? Would that be
No.
problematic?
No. There are infinitely many possible representations. Do you understand what I am saying or not?
So in a time signal,
Yeah.
we are losing the information of time itself if we do this, right? Or in a space signal, we are losing the information about space itself if we view it as a n-dimensional one point.
That is true. Yes, that is correct.
How can we do this? Because then we are forgetting our axis of signal itself. is
Loss
my
of
point.
information.
Because where what this is a problem you should have asked me, like in any lecture from lecture number 2. We have been converting signals to vectors for 4 lectures now.
Yes, but there one point was one sample.
No. The entire signal was one point in a high dimensional space. Okay. Okay, hey, just a minute. I need to take this poll because otherwise then, how many people understand the statement that the entire signal with all of its time-based values is a single point in a high dimensional space? How many of you understand this? So then what is the controversy? Everyone is raising their hand. Wait, then we'll come to that. See, your issue of losing time, that is correct, and which is why wherever you need time, you have to semantically add it in a different fashion. For example, which is why you get a special thing called a Toeplitz matrix. And the Toeplitz matrix has a special organization, and that speciality is there because it has to follow shift invariance. So we add it back using various mathematical tools, okay? But it has always been a single point in all the lectures till now, okay? Well, okay, now your problem, which sounds simpler to me. Okay, that is simple. What I did was, I took the first vector value, I projected it onto 2 axes. I chose like these axes. I'm going to call them horizontal and vertical axes, okay? I chose these horizontal and vertical axes. And imagine they are the same axis in all the planes because, I mean, I am standing in one place and doing the signaling. So whatever are those axes were attached to my reference, let us say. So you have these axes. Then I projected this value onto this axis and this axis. And then I get 2 numbers. And I take those 2 numbers and I put them consecutively one after the other. Okay? So sorry if I was not clear about that. So these 2 numbers are together representing the first vector valued sample. These two numbers are together representing the second vector valued sample. These two numbers are together representing the third vector valued sample. Okay? Yes.
Can we also have another representation where
No, don't, please don't. You can, but let's not. You can represent a thing in infinitely many ways mathematically. Okay? Or ask me in the break. Okay?
Oh, so he was saying when we represent in a six-dimensional,
Don't add representations.
when we do it in a six-dimensional space, we use a time value. But when we're doing it in a computer, we're using a array and that has an index, so that gives back the natural time value, right? Like theoretically we use it, but practically we don't. Or
I mean, there's a least count of time.
Yes, you are all right. You are all correct. You are all correct. And if we had infinite time, I, I would spend 3 more hours explaining whether these are the same things or not and the philosophical implications of all of these things. But yes, you are also right. You are also right that the time is lost. He is right that the time can be recovered. So it's fine. Is okay? Okay. Now, let's come back to our problem, which is much simpler than all of these philosophical discussions. Let me say this is the signal that was transmitted. Okay, can't say spoken anymore, transmitted. And let us say that there was some signal that was received, and that would be some other signal. Okay, some other signal was received, let us say, and we'll call that signal X. For the time being, from our problem, let us remove the problem of delays. We have done this before, right? We removed the problem of delays, we figured out what to do with scaling, then we added back the idea of what to do with delays as well, correct? So we are going to have to do the same thing again. So delays are again gone, which means only scaling remains, which means what? We are going to try to find out the best scale of u to fit x. Okay? Something like this, okay? So I am going to call the numerical representation of the vector valued signal, let me give it a name, this. How would you like to pronounce this? You are using both u prime. I will say u prime, is that okay? U prime, nothing to do with prime numbers. This dash is called a prime for some reason. Or u dash, if you know it as u dash, it's u dash. I got used to saying both things, so I might say both things. So u prime, okay? U prime, which is just saying u dash, okay? So this will be called x dash, x prime, sorry. Okay? Now, your problem is to scale u to fit x the best, correct? To come as close as x to x as possible. This is still not mathematically well defined. We'll define it better in a moment. Okay. First of all, let's try to think of what it means to scale u. What would be 2 times u, for example? Right. So every vector component should become 2 times. Okay. That would make the signal, vector valued signal 2 times. This will be our definition of scaling a vector valued signal. Okay. So then what will happen here? Every number will become 2 times. Agreed? What if this, I am scaling this vector valued signal by half, let us say, by the scale half? What will happen in its representation? Every value will become half. So this is very interesting. Scales here become vector scales or even signal scales here. Okay? That's a good thing because we already know how to deal with scales. Right? So now if I ask you the best scale of this to fit this, an equivalent question would become what would be the best scale of this to fit this. Agreed? But there is another slight issue, and that slight issue is, what do you mean by fit, or what do you mean by fitment? Which of the vectors comes closest to x? What do you mean by that? Remember, when we were thinking of just normal signals and saying scale one of the signals to fit another signal, among all the various possible scales of the signal that is being scaled, what is it that we chose? We chose the one that keeps the least error, but we had a specific way of measuring error, which was adding up the squares of the individual values. Okay. So let's try to do the same procedure here. If you have some scale of u, let us just say 1 times u for the time being, what would be the error between that and x? What would be x minus u?
Take the difference on the axis and then take the square and then take the square root.
Individual components.
So one simple way to think about it is individual components you subtract. They are all vectors, so they have a subtraction. So you subtract vector by vector. Okay? Which creates what in this picture? Each element gets subtracted. So it creates vector subtraction here, which is nice, isn't it? As many things as get represented as vectors, as normal vector operations, we are happy about that. Okay. So now if I say x minus half u, in this picture what you are doing is scaling all the vectors to half, and then in every plane you are subtracting the x vector from the half u vector. Sorry, the other way around, the half u vector from the x vector. Okay. In this picture what is happening is you are scaling every number to half and then just subtracting these numbers from those numbers to get a new set of numbers. It is still a set of numbers. Okay. Coming back to this picture, now you have this error which is itself a vector valued signal. A subtraction of one vector valued scale signal and a scaled vector valued signal is still a vector valued signal. Now you want to say that, oh, I want that to be a minimum, right? And how might you say that? Vector valued signals. So every value is a vector. You want to say that, oh, let this be as small as possible. Let this vector valued signal be as small as possible. That's a good idea. Sum of the lengths is a good idea. But what's a slightly better idea? Sum of lengths of individual components. Okay? Why is it better? Because squares are easier to calculate with. Okay? Question? Right. So our sense of what we are minimizing is going to be, we are going to minimize the sum of squares of lengths of individual components of the subtraction of the target vector valued signal and the original vector valued signal that is being scaled. Okay? Sum of squares of lengths of individual components of the error vector valued signal. Is that okay? Now, for the time being, let me just draw a third vector valued signal. And let's say that this is that error signal, okay? This is some error signal here. And it's got a representation something, something, something. Sum of squares of lengths of these vectors is what in this representation? Sum of squares of lengths of those three vectors is what in this representation? Sum of squares of all these numbers. And how did that come about? By the
Euclidean jumped it because a point.
but it's got a name to it. Pythagoras theorem. Correct? Slightly before Euclid, so you should give him preference. Pythagoras theorem. Did you get it or no? Was this okay or no? Did you get the Pythagoras theorem thing? So basically, so this is your error signal here. Now, what is the square of the length of this thing? The square of the length of this thing is the square of its horizontal projection plus the square of its vertical projection. That's Pythagoras theorem, correct? This much you remember? But the horizontal projection is this and the vertical projection is this. And so the square of the length of this value is the sum of the squares of these two values, correct? And so the square of the length of all of this is actually the squares, the sum of the squares of these numbers. The sum of the squares of all of these, sum of the squares of the lengths of all of these is the sums of the squares of these values, correct? So now if we are taking this vector valued signal and finding its scale and trying to fit another signal such that the sum of the squares of the lengths are minimized, what happens in this picture? What happens in this picture is you are scaling these numbers just by vector scaling to try to fit these numbers which are not scaling. You are trying to make them come as close to these numbers as possible. And what do you mean by as close as possible? You are minimizing the sums of the squares of the errors between the two. We already know how to solve that, don't we? Inner product. Yes, differentiation, but you don't have to go through the whole thing because we solved it before. Right? Did it just scale a vector to fit a vector the best? Minimum sum of squares. Correct? Minimum sum of squares is just another way of saying minimum error, length of the error. geometrically. Because the sum of squares of these numbers is nothing but the length square of this 6-dimensional vector, geometrically. Agreed? By Pythagoras theorem. Correct? And so you know how to solve that, right? And how do you solve that? The best scale of u to use is u prime comma x prime upon u prime comma u prime, correct? Yes? So we solved a very different setting using the same mathematics, right? We solved a extremely different kind of setting by using the same mathematics. This, by the way, there are various realistic communications protocols that have used vector valued signals. So, it doesn't have to be with skipping ropes. For example, people have, do you know that the physics of light is somewhat like the physics of skipping ropes? Physicist? Okay. How are they similar?
So, like the electromagnetic waves can be thought of as a
Skipping rope.
skipping rope, exactly.
Yeah, in the
They are the same because both skipping rope waves and electromagnetic waves are transverse waves. Sorry, longitudinal are number valued waves, and electromagnetic and skipping rope waves are vector valued waves. And so people have actually attempted to create electromagnetic signaling mechanisms which use the transverseness of light. Okay? And there are other things also which can also be thought of as vector valued signals, and there's a lot of things. If you ever study the 5G protocols, they are using various kinds of vector valued signal kind of ideas, which is how they manage to push so much data, much more data than you could have before, so that you can see even more reels in real time. So more people can see more reels in real time. 5G using vector valued signal. So all of this does have some real world applications.
Even if they are transverse waves, they need not, like, they need to be two-dimensional transverse waves particularly, right?
I mean, currently we did it for 2 dimensions, yes. So you can try at home whether this will work for higher dimensions. We are not going to.
Like, I don't understand how the transverse nature of the wave is coming into picture in any way.
I mean, this is how skipping rope. The skipping rope is moving. That's where the word comes. Skipping rope is moving transverse to the direction of movement of the wave. That's where the transverse nature of the wave is coming from. Okay. Is okay?
So, skipping rope is like transverse wave and vector valued. Each sample is a vector value.
Yes.
And sound wave is longitudinal wave and each sample is number.
A number, yes. Thank you. Yes, what he said, yes. So we did all of this, okay. My friend and I did all of this so that we had the correct scale, so that he knew that he was hearing at a different scale, so that we didn't have misinterpretations of each other's signals. We were in the second standard. We did all of this mathematics because it's all additions and multiplications, isn't it? After all, we had learned it by the second standard. Anyway, so then that night again I signaled to him. Still got it wrong. Couldn't figure out what is happening. There was another issue. My house and his house were tilted with respect to each other. Slightly different parts of Earth, gravimetric distortion, call it what you will. My house and his house were tilted with respect to each other. Okay? This is okay? In that 7-foot distance between my house and his house, there was enough of a tilt that not only was there an unknown scale between what was sent and what was received, there was also an unknown amount of rotation, okay, in the signal. So now our problem becomes we are still disregarding delays. So there are no delays, but now we have scales and rotations. Okay. Shall we for the time being disregard scales? Let's disregard scales for the time being and only concentrate on rotations. So just think that this signal is being rotated. What happens if you rotate it by 0 degrees? Nothing happens. What happens if it's rotated by 360 degrees? Nothing happens. What happens if you rotate this signal by 180 degrees? What do you mean by rotating a signal by 180 degrees? You are rotating each of its vector samples, because it's a vector valued signal. You are rotating each of its vector samples by 180 degrees. So can you imagine that? So what happens is this sample goes like this. This sample goes like this. This sample goes like this. The question as always is what happens in this picture if there is a 180 degree rotation. All the numbers flip, invert their sign. Agreed? Which is something we have already accounted for in our earlier this thing, right? It was a scale. So rotation by 180 degrees is just a scale, isn't that nice? So that was already accounted for. So we did 360, we did 180, we did 90. No, now let's do 90. So if now let's say that I rotate this signal by 90 degrees. Okay, and just for some convention, I am going to rotate 90 degrees this way, which is counterclockwise look when you look from this side. Okay, you have to set up some convention. So this will become something like this. This will become something like this. This will become something like this. Okay, your vector values are all rotating by 90 degrees. Agreed? What happens in this picture is my question. Okay. So I am going to call this rotated signal U tilde. Okay. That swing on top is called tilde. U tilde. The corresponding signal here should be called U tilde prime. Okay. So let's try to find the 6-dimensional representation of the rotated signal U tilde. Now what he is claiming is, say that once again, so what do you think? The values switch in pairs. No, second here or second here? Okay, so let's look at this. So when you, okay, let's draw it head on so that it's easy for us to see what is happening. I'm just drawing one plane head on. Is that okay? So if I draw it head on and I have this value, it rotates 90 degrees to produce this value. And so the first thing that you see is what was the horizontal component, that same number becomes the vertical component. Okay. So the horizontal component was the first value here, correct? So the first value here becomes the first value here, correct? And what was the vertical value now becomes the horizontal value, but with a sign flipped. Agreed? This will work in all quadrants. You can try it yourself. It will work in all quadrants. The sign will flip always. So what was the vertical value becomes the horizontal value, but with the sign flipped. Since in every plane you are rotating by 90 degrees, the same procedure will happen in pairs all across. Okay? What was the horizontal value will become the vertical value. What was the vertical value will become the horizontal value flipped. Is okay? Correct? Sorry, did I do something wrong?
The last one should be last in both.
Sorry. Okay? Okay?
So the vertical is becoming horizontal and horizontal is becoming vertical with sign.
No, the other way. The horizontal is becoming vertical. The vertical is becoming horizontal with a sign flip. See, look at this. The horizontal becomes the vertical. We are rotating this way, yes. Then it would be what you said, yes. But for convention, we chose to rotate this way. We are seeing what happens in a 90 degrees counterclockwise turn. Okay?
There the horizontal will become vertical
Yes,
and vertical will become horizontal with sign.
with sign flip. And this specific thing is happening because also by convention, vertical is counterclockwise to horizontal. All by convention. Yes. Okay. Is okay? Now I ask you the next question. We did what? 360 degrees, 180 degrees, 90 degrees. What should we do next? 270. Let's do 270. Okay. Random degree, yes. Eventually, yes, we have to get there. 270 is okay. 270. What about 270?
Mirror image.
You can think of 270 as 90 and then 180. But 180 is just a flip of the whole thing, which means that you could flip this and get 270. Correct? Right? Which means 270 has that other rule that you said, that horizontal becomes vertical flipped and vertical becomes horizontal. It makes sense. Let's do 45 degrees. 45 degrees, huh? So,
Whatever you said here that x will become y and one of the signs will flip, that will work only if the signal is in first and third quadrant.
no, it will always work. It will work in all four quadrants. I said it in an offhand remark that it will work in all four quadrants. You try it, it will work in all four quadrants. Or in the break, let's sit and, or you, if it doesn't work, you show me. Okay? It will work in all four quadrants. I'll give you a homework in every quadrant. So, this, convince yourself. Okay. 45 degrees. 45 degrees. Now, if this is the original, this is the 90 degrees one, here you have the 45 degree one, correct? Correct? Here somewhere is your 45 degree one. Okay? 45 degree, 45 degree, 45 degree. Okay? What about it? Yeah, you could calculate it. I am sure you gave your JE or something. Yeah, Lowney's trigonometry, does that still exist? It still exists? Lowney's trigonometry? You know, my grandfather studied from it. Anyway, so you could use that. Is there a simple trick? Look at this diagram. Is there a simple trick? Yeah, it kind of looks like the average of this and this, right? But not exactly. But it is exactly something.
It's the sum of the 0 and 90 rotated vector.
It's not the sum either. It's not the average either.
With the average multiplied by some factor.
It's like scaling 0 to 90.
By with 2.
Correct. What is this? As vectors. It's root 2 times this vector plus root 2 times this vector, isn't it? Ah,
No, 1 by root 2 times.
sorry. Sorry. Yes. 1 by root 2 times this vector plus 1 by root 2 times this vector. Correct? Why?
We can shift the coordinates since they are perpendicular. Use.
That's one way to think about it, yes. Or you can just say that sine 45 and cos 45 are both 1 by root 2. That's where this came from. Okay? Correct? So this vector is 1 by root 2 times this vector plus 1 by root 2 times this vector. Correct? Does the same thing apply in all your planes? It does. Yes? So what happens in this picture? You scale this to 1 by root 2, scale this to 1 by root 2 and add both of them and you get the exact representation of the orange point, of the entire orange signal, the 45 degrees rotated signal. Now what if I give you 30 degrees?
Uh, just clarification. 1 by root 2 of the 45-degree vector will be given to 90 and the original value.
Sorry, 1 second. What? 1, no. 1 by root 2 times this plus 1 by root 2 times this equals this. Okay? Now, if I rotate it by 30 degrees instead of 45 degrees, what will happen? Correct. Root 3 by 2 and 1 by 2. Of these two, do you see that any angle is going to be a scaling and an addition of these two? Correct? If I am scaling by some angle theta, how much of this do I use and how much of this do I use? No, just cos theta and sin theta. Okay? How much of this do I use? Cos theta times this. And how much of this do I use? Sin theta times this. Agreed? Agreed? So, so if your question was, let's take that u, let us rotate that u, and try to find the rotation that fits x the best, then what does that question lead to? That question leads to, let's find the theta such that this scaled by cos theta plus this scaled by sin theta comes closest to x dash. Agreed? Which is a tricky problem to solve, because you have to find the theta. But, what is the original problem? The original problem is not just asking us to find rotations, it is asking us to find rotation and scale. So now, rotating the vector by theta gave you u prime scaled by cos theta, u tilde prime scaled by sin theta. Now furthermore, let's scale that rotated vector by some amount, okay? And let's say the scale is a. So I am furthermore now using a scale of a, where a is unknown. We are going to figure out what that a is. Small a, small letter a. So now u prime scaled by cos theta plus u tilde prime scaled by sin theta further gets scaled by a. What does that mean? What does that mean? What does that mean? What? Okay, I'll tell you what that means. Correct, but there's another even better way of thinking about it.
A times some signal, some z plus some noise is equal to a final x. And we are now trying to fit. We are trying to solving the same problem now which we had solved before.
Yes. Okay. Huh?
Just A and B, it's a linear combination of A.
That's okay. But there's a step in between. Okay. You people can never give me the correct intermediate step, man. Either you are too short or too long. Like ballers. Cricket. Okay. So, okay, when you are only rotating, your options were cos theta times u prime added to sin theta times u tilde prime, correct? Correct? Now furthermore, you are allowing this itself to scale by a, correct? Because if I scale this orange vector by a, then its representation also scales by a, correct? Which means you are scaling this by a. But scaling this by a does what? It actually scales u prime by A cos theta, A is a number, cos theta is a number. This is just a multiplication. So A cos theta is just a number. You are scaling U prime the vector by this number and scaling U tilde prime by this number. Okay? Right? And so now when you say that I have to find the best scale and best rotation, you have to find theta and A such that when I put in that theta and that A, this vector comes closest to x. Yes? But let me just call this something, let me call this alpha. It's a number, let me call it alpha. Let me call this beta. And then this just becomes alpha u prime plus beta u tilde prime. And let me say that, oh, let me just find alpha and beta such that alpha u prime plus beta u tilde prime comes closest to x prime. Does this make sense? Why does this make sense? Because given alpha and beta, can you recover A and theta? Yes. How much is A? The square root of alpha square plus beta square. And how much is theta? Tan inverse of beta by alpha. Correct? This is what? Rectangular to polar conversion. Agreed? So you can think of these two things that you are trying to find out, the gain and the rotation, as polar coordinates of a scale whose rectangular coordinates are these alpha and beta. And find alpha and beta instead. And why would you love to find alpha and beta instead of A and theta? Because we already know how to do that. Right? What is the best addition of two scaled vectors to match a third vector is something that we have spent hours trying to figure out. The pseudo inverse formula. Correct? Just one more short thing and then we'll take a break. Now, to do the pseudo inverse formula, what do you have to do? So now you know alpha and beta are to be calculated by the pseudo inverse formula, correct? To calculate the pseudo inverse formula, there are two things. There's a square matrix and you have to take its inverse, and then there is another vector of inner products, correct? Agreed? You remember pseudo inverse formula? The vector of inner products is going to do what? U prime inner product x prime and U tilde prime inner product x prime. And the matrix that you are going to invert is going to have what? U prime dot U prime, U tilde prime dot U tilde prime, and then U prime dot U tilde prime, correct? In the cross diagonal, off diagonal terms. Yes? Let's calculate that first. There is one proposal. So that's my question then. What is U prime comma U tilde prime?
They are perpendicular by much.
Yeah, kind of, and it kind of works, but it's still, let's still calculate it. U prime comma U tilde prime, right? How do you calculate inner product? Just multiply and add. Do you see what happens if I multiply these numbers and add all of them together? what happens is that this times this cancels with this times this, because they are the same magnitude and opposite sign. Correct? Similarly, this times this cancels with this times this cancels with this times this, and so u prime comma u tilde prime is 0, is 0. Okay? Which means as vectors in 6-dimensional space, these two vectors are perpendicular to each other. If they are perpendicular to each other, we get a especially simple version of pseudo-inverse, which is what? You can just drop perpendiculars to them individually and add that up. Correct? We have done all of this in previous classes. We are building on what we did in previous classes. Agreed? And so, you get that alpha equals this u prime x prime upon u prime and beta equals u tilde prime x prime upon u tilde prime u tilde prime. Is okay? Once again, quick recap. We are trying to find the best rotation and scale of u to u, which is a vector valued signal, to fit another vector valued signal x the best. And we found that how do you do that? You do that by calculating this alpha and beta using these formulas and then converting from these rectangular coordinates alpha and beta to the polar coordinates a and theta, and a is the best scale to use, theta is the best rotation to use, is what we have found till now. Okay. We have done something absolutely amazing and beautiful, but you don't know that yet, and you have to wait for 5 minutes, take a 5-minute break, and we'll see what we have actually done. Okay, this is where we were. We are rotating and scaling a u, to fit an x. U prime is the numerical representation of u. U tilde is rotated u tilde prime is its numerical representation. And we figured out that to do that, we have to find the best scale of u prime and u tilde prime. So, alpha u prime plus beta u tilde prime would be my best fitment, correct? Yes. And we found that the best alpha and beta to use are these things. Why? Because alpha and beta, because u prime and u tilde prime are perpendicular to each other. Agreed? So, now let us see what we have done to make my next point. It will be easy if I just use some numbers. So, let us just say I have some numbers here in my signal, and then there will be corresponding numbers here. Do you agree? -4, 1, 2, -3, correct? Now, see that I am going to use alpha times this plus beta times this, correct? So, if I have found the correct alpha and beta, then in this representation, my best fit is going to be alpha times this vector, right? Alpha scaling this vector 3, 2, 1, 4, -3, -2 plus beta times this vector minus 2, 3, minus 4, 1, 2, minus 3. Do you agree? So, let us actually just calculate it. Humor me for a moment. You get this alpha 3 minus beta 2, right? Alpha 2 plus beta 3 and so forth. Agreed? If you look at these two, the first two numbers, alpha times 3, alpha 3 is alpha times 3. I know that that's a strange way to write it, but it's okay, it's just multiplication. If you look at this, these two numbers, alpha 3 minus beta 2, alpha 2 plus beta 3, these are two numbers, correct? Right? Alpha 3 is just alpha multiplying 3. There's nothing strange happening. These two numbers are representing what? They are together representing, yes, the first vector valued sample in the best fit scale rotate of U. Agreed? These two together represent the first vector value. These two represent the second vector value. These two represent the third vector value. Correct? Now, this, if you think about it, if I gave you these two numbers, 3 and 2, what are 3 and 2? They represent the first vector value of U. Agreed? And if I gave you alpha and beta, you will be able to calculate this from that. Agreed? If I just had these values with me, I will be able to calculate these two values from these two pairs of values. How? Just this times this will be this, and then I subtract this times this, and that gives me the first value. And this times this plus this times this gives me the second value. Okay? So this is like some kind of, this is some new kind of operation which takes two entry vectors, two entry vectors, and produces another two entry vector. Let me represent it by some fancy symbol. Okay? Agreed? So this fancy symbol is what operation is this times this minus this times this as the first output, this times this plus this times this as the second output. Okay? Is it okay? And then this same fancy symbol, instead of 3, 2, if I apply it to 1, 4, I will get the next two terms. If I apply it to minus 3, minus 2, I will get the final two terms. Correct? Agreed? I am going to come up with some fancy notation. In this thing, these are two entry vectors, right? So I will give unit vectors for two entry vectors some special name. I could call them anything. I am going to call them boldface 1 and boldface I. Okay? Mathematics, I can do anything. Boldface 1, boldface I. Agreed? Now, if I call this boldface 1, call this boldface I, this alpha beta is now represented as alpha times boldface 1 plus beta times boldface I. Agreed? 3 2 is represented as 3 times boldface 1 plus 2 times boldface I. Agreed? Yes. And then this I can write it as alpha times boldface 1 plus beta times boldface I. Fancy operation, 3 times boldface 1 plus 2 times boldface I gives what? Alpha times 3 minus beta times 2 into boldface 1 plus alpha times 2 plus beta times 3 into boldface I. Okay? What is this? This complex multiplication. Okay? What we were calling skipping rope is called complex numbers. We'll see what this is in a moment. It's going to take me some time to explain. This just begins, okay? First of all, do you see that at least the rule is the rule of complex multiplication? You agree? We kind of remember it as I times I is minus 1 and that's how you get this. And that's one way to think about it, yes. Okay? And you can calculate it using that rule that you remember. Huh? Now, it is somewhat traditional that what we are calling the horizontal axis and the vertical axis is called the real axis and imaginary axis. Okay? That is a strange thing to say because imaginary numbers are as real numbers. To be more specific, all numbers are imaginary. Okay? All numbers are imaginary. So calling some specific thing imaginary is strange, but we get used to that notation. I mean, whatever. So, complex numbers are just points in a plane. They add like vectors in a plane add, and they multiply using this special operation. Okay? Is that okay? Complex numbers are just points in a plane that add like vectors add. That's what we have been doing all the time, right? Add like vectors add and multiply using this special operation. What does this special operation do? What it is actually doing is see, here's how we are thinking about it. You are taking a vector value and scaling and rotating it. Yes? So that's what complex multiplication, this fancy operation is called complex multiplication. And what is that? That is just taking a vector value and scaling and rotating it. You are scaling it by what and rotating it by what? You are scaling it by square root of alpha square plus beta square and rotating it by tan inverse of beta by alpha. Okay? This is what complex multiplication is. Another and a simpler way to think about it, something that you probably have heard about before, is how do you multiply two complex numbers? You multiply two complex numbers by multiplying their magnitudes and adding their arguments. You remember this? Multiply magnitudes, add arguments. That's all we are saying, right? Scaling is multiplying the magnitudes, and adding arguments does what? Rotates the complex number by whatever is the argument. No? So instead of thinking of this as alpha scaling u prime and beta scaling u tilde prime, we now think of it as alpha beta being one complex scale, complex scaling a complex signal. Alpha comma beta or alpha 1 plus beta I is one complex scale, complex scaling a complex signal. And by complex scaling, what is it doing? It is appropriately rotating and scaling that signal. By doing what? By doing a complex multiplication in each plane. Okay? Let us calculate what that complex scale actually is. Okay? Alpha bold case 1, beta bold case I is the complex scale. Agreed? By the way, in usual notation, for some reason, you drop the bold case 1. It's implicit. It is there. Now, every time you see a complex number, remember that there is a bold case 1 next to something I. What is, if this is something I, this is something what? Has to be answered. And so, I am writing it explicitly as bold case 1. It is there. Okay? Okay? So, your textbook writes this as 3 plus beta I. But 3 of what? 3 of something. And that something I write as bold case 1. Okay? Some people like to claim that that is the real axis. But that's, if you take it literally, that is not true. Because the bold case 1 is not actually the real number 1. It is the vector 1 comma 0 as we saw before, which is not the real number 1. And just structurally, if you think about it, mathematically, you cannot have real numbers sitting inside complex numbers. Why? Because complex numbers are built out of real numbers. Just like you actually cannot have fractions sitting inside real numbers. Why? Because real numbers are built out of sequences of fractions. You cannot actually have natural numbers sitting inside fractions. Why? Because fractions are built out of natural numbers. So even though in school they taught us these things as extensions, actually they are completely different mathematical objects. Similarly, complex numbers are actually a completely different mathematical object than real numbers. They are not an extension of real numbers. Okay? The one part of complex numbers behaves like real numbers, so we kind of get used to calling them real numbers. Because if nothing is rotating, then everything is only scaling, then it behaves like real numbers. Okay? So we treat it like real numbers. But literally speaking, they are not. Okay? Just think of it from a computer point of view. How much storage will it take to store a real number? How much storage will it take to store a complex number? It will take different amounts of storage. So one of them is not just part of another. There are two different types. Okay. So alpha 1 plus beta I. What is alpha? Alpha is that. Correct? U prime x prime by u prime 1 plus u tilde prime x prime u tilde prime I. Agreed? Okay. So, okay, first thing we are going to see is that what is this u prime? U prime is this. Is 3 square plus 2 square plus 1 square plus 4 square plus minus 3 whole squared plus minus 2 whole squared, correct? What is u tilde prime? U tilde prime? Minus 2 square plus 3 square. Same value. You agree? Same value. So I'll pull it out. One upon u prime, okay? I'll pull it out. So now I have u prime x prime 1 plus u tilde prime x prime I. And now let's expand that. What is that? So this is 1 upon u prime. What is u tilde prime dot x prime? What is u tilde prime dot x prime? So, sorry, not u tilde prime, sorry, u prime dot x prime. It is going to be 3 times the first number in x prime. But what is 3? The first number in u prime, but which is the horizontal component of the first vector in u. Agreed? And so I am going to say that this is u1 horizontal component, right? So the horizontal component of u1, these are u1, u2 and u3. And here the first thing is u1 horizontal component, which I'll call it u1r to honor traditional notation, real part of u1. Okay? Real part of u1 times real part of x1, x1r. And then when I multiply this to the corresponding value of x, what do I get? No. What is this? This is u1i, imaginary part of u1. Okay, real part, imaginary part. Okay, are the two projections. Horizontal projection, vertical projection is now called real part, imaginary part. So u1r x1r plus u1i x1i plus u2r x2r plus u2i x2i plus, right? And so forth. Yes, correct? This is the one component, agreed? This is the one component. This. And now let's calculate the I component of the same thing, of the same term. Do it. U tilde prime dot x prime, calculate it.
U tilde 1 r x tilde x 1 r.
Where did the I term come from?
See, what is U1? U1, U2, U3 are the three components of U. You can use the three components of U tilde, that's correct. Because U tilde is here, it has three components, you could do that. But let's use the three components of U themselves.
Minus u1 I.
Yes.
Yes, go ahead. Is it? What is it? So, it's going to be this, correct? Which is minus u1i, you are right, minus u1i. So, minus u1i multiplying what? This hasn't changed, so that's going to be the same. Multiplying x1r plus what? u1r, no negative sign, u1r x1i plus, sorry, minus u2i x2r plus something and so forth times I. Agreed? Agreed? Let me bunch it a bit. This equals, the reciprocal remains the same. I am going to rebunch this thing into u1r x1r plus u1i x1i 1 plus minus u1i x1r plus u1r x1i I. Okay? Plus the terms for 2 and terms for 3 and so forth. Is it okay? I have just rearranged things. Okay? Now look at this whole thing here and give it a name. Not u and x. Is it complex multiplication of u1 and x1? No? What is it? It is actually u1r1 minus u1i times x1r1 plus x1i. This equals this. Convince yourself. I need to convince myself as well. Did we get it right? Huh? Right. Yes? What is this? This is the complex conjugate of U1. And what is this? Just the complex number x1. And so this whole big thing is just U1 conjugate x1. Okay? U1 conjugate x1. Okay? Which one?
U1RX1RX.
Yes. The how you went from the third last step to the second last step.
Here to here? Just substituted. I just looked at the numbers in U prime, numbers in X prime and just wrote it down. Yes, absolutely. U1R is a real number, X1R is a real, these are all real numbers, these are all real numbers. Yes, that so that one I is just my notation. U1I is a single number which is a real number. It's not complex. Huh? What? No. Yes, U1I is the vertical component of the complex number U1. Nothing to do with the tilde. Ah. Agreed? Okay, go ahead again, do this very carefully, okay, because you have to chase through this argument to get it right, and you have to carefully understand the types of everything because it's quite tricky. Complex numbers show up here, right? U1 and X1 are complex numbers, but U1R, X1R, all of these are real numbers. Okay? We did to get the components of U tilde prime out, we did momentarily look at this, but then we directly substituted the fact that the first component of U tilde prime is going to be minus U1I. And so directly we wrote here minus U1I, which he was pointing out that it is U tilde 1R, which is correct. So this is plus U tilde 1R, and we skipped a step and directly wrote minus U1I. U1I is also a real number. Don't be confused. The imaginary component is just a component on the imaginary line. It's a length, it's a number. It is not itself an imaginary number or even a complex number.
Why are we doing all this if we were able to represent it in vector form?
Why we are doing this will become clear after we chase the whole argument till the very end. That we don't know yet. Shall we chase it to its very end? Few more steps, almost done. Okay. And so now I see that this equals 1 upon that thing, whatever that is, times this U1 tilde x1 plus such other terms which are what, just U2 tilde x2, U3 tilde x3, how many ever components you have, okay? We have only 3, so U3 tilde x3, but if it was more components, you would just do it for more components. Agreed? I give because I have 3 planes there. Arbitrary choice that I made at the very beginning of the lecture. My arbitrary choice had 3 time samples. That's all. That's where 3 came from. It could have 10 or 100 or 1,000 time samples. Correct? I just didn't want to draw all that much. So I took 3. And if I had taken 2, I would have really confused you because something else has 2 components. So I took 3. Okay? Okay? This is okay. Very important thing happens here. We give this a new name. We are going to call this U inner product X. Okay. This has never been defined. In fact, this is very different. This is not, see, till now, all the inner products were with primes. Why? Because we can take inner products with primes because those are vectors that we know how to take inner products with. U and X are vector valued signals. Now we will call them complex valued vectors, and we are defining, right, complex valued vectors or complex entry vectors, and we are defining a new meaning of the inner product formula. It's a new meaning of the inner product formula for complex value vectors. And what does it do? It does take components and adds them, takes components, multiplies and adds, but it does one extra strange thing. It takes the conjugate of the vector on the left. Okay? So you don't just multiply and add, you conjugate the left vector and multiply the components and complex add them together to produce a complex number. Okay? And that produces this U comma X. This is a new definition. Anyone of you has done like quantum physics? Quantum physics, anyone? Quantum physics? Everyone mostly has done quantum physics. It's a compulsory course. Have to do it. Remember the bracket notation? Remember there's an integral and there's a strange conjugation happening for no particular reason? Now you know the reason. Okay? That's why the conjugation is happening in that strange bracket note. Instead of a comma, they use a vertical line, but they are doing the same thing. Remember bracket integrals? You had this, no? If you took a compulsory course, you did something like this. Bracket P bar Q equals integral Pu conjugate Qu D, whatever is your space. Why did that happen? Now you know why that happened. Why did you conjugate the left side? You conjugated it because that is what allows you to fit one vector to another vector the best. Okay? Almost there. Almost there. Almost there. Now we have to deal with this because that is still U prime comma U prime. Okay, that is still U prime comma U prime. What is U prime comma U prime? U prime comma U prime is this 3 square plus 2 square plus 1 square plus 4 square plus minus 3 whole square plus minus 2 whole square. Calculate U comma U. Now you can, because we just created a new definition of complex value vector inner product. Correct? And what will that give you? That will give you u1 conjugate u1 plus u2 conjugate u2 plus u3 conjugate u3. How many ever components you have? Correct? What is u1 conjugate u1?
U one inner product of u1 and
u1 r square plus u1 i square.
Hmm?
u1 r square.
u1 r square plus u1 I square. Why? Because u1 tilde u1, same magnitude, opposite arguments. Correct? I mean, same real part, opposite imaginary parts means same magnitude, opposite arguments. If you multiply them, special operation multiply, the arguments add, which means they cancel out. You have only the horizontal component and its magnitude is the same, which means that you get the magnitude squared. Sorry, not this. This is the magnitude squared of u1. Remember this. u1 conjugate u1 is just the magnitude of u1 squared. Complex numbers, not saying anything new. But the magnitude of u1 square is u1 r square plus u1 I square. Pythagoras theorem. Correct? And so this equals u1 r square plus u1 I square plus u2 r square plus u2 I square and so on and so forth. Isn't it? Isn't it? No, not really, not really, not really. Times 1 plus 0i, that's what it actually equals. Correct? To be precise, because the type is still the type of a complex number. You multiply to complex number, you get a complex number, you add complex, you get a complex number, this is still a complex number. Right? So this equals what? This equals u prime comma u prime, because that's what this is, u1 r square plus u1 I square plus u2 r square plus, is u prime comma u prime, correct? Times 1 plus 0i. Okay. Now, if I were to write this as 1 upon u prime comma u prime multiplying u comma x, that is one thing. That is one thing. What does this mean? I take the complex number u comma x, which is a vector, and I scale the vector by a real number. I know how to scale vectors by real number. This is a real number, I do that. I am going to claim that this equals, I am going to claim that this equals ux by u. Okay? And why is that? Anybody? You have to correctly define complex division to be the inverse of the special flower power complex multiplication that we saw, which we defined to be some arbitrary thing which helped us. The inverse of that, you define it to be division, and if you do that, then you get that this equals this. Why? Because then the inverse of this, the multiplicative inverse of this is what? Is the reciprocal of this times 1 plus 0 times I. Okay? And thus, with this is absolutely, did you see what we got? It's like we spent an entire lecture doing nothing, but that is not the case. We did something very brilliant. We got the same looking formula. This is the formula we finally got. The best scale and rotation of the signal u to use to come closest to x is u comma x upon u comma u, which is the inner product formula from before, but it only looks like the inner product formula from before. It's actually an extremely different thing. Absolutely. Not every step, but at least in one step, the comma was very specifically created. A new comma operator, this, was very specifically created to make this new formula look like the original formula. Okay. Yes. Do you remember, have you linear algebra, did you do like complex linear algebra? No? Really? Oh, okay. But don't you like ever remember that, like while, like if you have like something real, you take the transpose. But if it has got complex numbers, then instead of taking transpose, you also do conjugation while taking the transpose. Why? This is why. This is why. U comma is nothing but U transpose, isn't it? Remember we saw this. And so while taking the transpose, you have to do the conjugation. You never define transposes, you define Hermitians in complex operations. Why? This is the reason why. To get the best fit formula. So yes, we created an arbitrary new definition, is the definition we like because it creates a new best fit formula, and we like best fitting because the entirety of data science and signal processing, quantum physics, everything ever depends on best fitting. Just a quick recap, complex best fitting is very much like real best fitting, but one complex axis or one complex vector, when scaled and rotated, actually creates a linear combination of two real vectors scaled. And two real vectors scaled produce what? Produce a plane in a high dimensional space. And so one rotating complex vector actually produces geometrically a plane in a high dimensional space, and finding a point in that plane that comes closest to another point, which is our target point x, turns out to be an operation which we now call the complex inner product formula or complex correlation formula. Okay?
So again, why did we need it? Why couldn't we do it with just two vectors and their linear combination?
Yeah. So we did nothing new. You are right. Did we did this? We did not need this. I could have cut out the last half of the last half hour of the lecture. This is notational convenience. Okay, and once you get used to it, you start just twiddling things around. You just like a transpose mein Hermitian lena. It's like you just get used to these things and they become fast to you. So which is why, for the notational convenience, and the entirety of textbooks in the entire universe are written using this notational convenience, that you always take Hermitians, which is why we did the last hour. You do not need it. The alpha and the beta and the alpha and beta formulas that we got was the actual end of the lecture. And you could rewrite the entirety of all textbooks in the world using the alpha and beta formulas. You do not need this formula. This is an artificial formula, but we get used to it. All books use it. We use it.
To do the calculations in another representation. So at first we started with the first representation in which it was u dash and u tilde dash and x dash, and then we did all of this calculations to go to u and x. So maybe the point may be that performing calculations in that representation might be easier. So there is a point to that.
Sure, but they are very slightly bit easier. You're right. Anyway, so yes, they are a little bit speed faster. Okay. Okay. Recap. Wait. Recap. Then ask me questions after the recap is finished. Okay. So once again, a complex vector is rotating and scaling to fit another complex vector. Geometrically, that is equivalent to finding a point on a plane. Okay. That plane is the direction of the complex vector. A direction is now a plane, not a straight line. Why? Because if you multiply the complex vector by the complex number, you get the entire plane. So the plane is now a direction. In that direction, you are finding the best point, which gives the complex inner product formula. The complex inner product formula will be put to beautiful and brilliant use in analysis of convolution, which is what we'll start doing next time. Then we go back to convolution and start learning what all of this has to do with analyzing convolutions in an extremely deep and beautiful fashion. Thank you very much. I will see you on next Thursday.